Good. So we are going to finish the last section. Then you'll be fully ready for homework and exam. And well, let me make sure what will happen this week. So today we will finish this note. And then on Wednesday, I'll try to review this chapter quickly and then discuss your question. And homework 7 is due Wednesday, midnight. So after you submit your homework, I'll upload the solution so that you can check your calculation. And then exam 2 will be given on April 3rd as planned. The exam will be available from 8 a.m. to 8 p.m. And you can start the exam at your convenient time, but you need to finish this in 60 minutes. I'm giving you 50 minutes plus 10 minutes because you need to write down your solution for free response problems and then upload your copy into ecampus. I'm giving you 10 more minutes so for this uploading your copy. I uploaded practice exam in ecampus. Did all of you take a look at practice exam?
Yes.
Good. So as you see, I'm thinking of giving you 4 multiple choice problems and 3 free response problems. Again, exam problems are based on homework. So for example, 4 multiple choice problems are based on homework 7, homework 6, I'm not sure. I think homework 6. And free response problems based on homework 7. So homework problems are very important. So let's take a look at practice exam quickly. Well, I'll enter problems in ecampus so that you can check your option for this multiple choice problems and then click submit button. For the free response problem, you need to write down your solution carefully on white paper and then upload it. The way you upload it is similar to, basically the same to the way you uploaded your solution for your homework. If you need extended time, you need to send me the letter from Disability Services, then I will set some extended time for you. Okay, so as you see, the first, well, let's take a look at this practice exam. Well, number 1 is about piecewise function, and you want to express, by the way, can you see this screen that I'm sharing?
Yes.
Yes.
Good, good. So first one is about piecewise function. So you want to express given piecewise function in terms of unit step functions. As we discussed in our note, if you understand how we find it, you should be able to find it quickly. There shouldn't be a big problem. Let's see. More students are coming. All right. So for those who just got in, well, this video is being recorded. You can check the first part that you missed once I upload this into eCampus. The video as well as note will be available in eCampus. Okay.
Oh my gosh, he chopped his hair off.
Well, the weather is getting hot, and I thought that so I just had my haircut. Yeah. All right. So number one is a piecewise function, and number two is partial fraction decomposition. If the denominator is a product of three distinct linear factors, you can find the decomposition quickly. You can apply cover-up method, for example. And number three is quite similar to the previous quiz problem. So you want to use first translation theorem to find this inverse transform. And number four is to use second translation theorem to find this transform. And then three more free response problems. I will choose reasonable numbers and functions and expressions so that your answer is also reasonable. And then number 7 is about Dirac delta function that we will cover today. All right, any question about exam format or exam in general? Any question?
Will we have to show our work for the multiple choice questions and submit those with the free response as well?
No, only for free response. So you choose your choice in eCampus. Once you click submit button, that's it.
So it's going to be like an embedded quiz within eCampus where we choose the selections for the free multiple choice?
That's right.
Okay.
Any other question?
Okay.
Are we going to get the tables for the Laplace transform on the exam?
Good question. I'll give you, so as I said, I'll give you formula sheet with the table of Laplace transform, all the theorems, first translation, second translation, and Dirac delta function theorem, everything. Another question? Okay, so then let's get started. I'm sharing our note. Where did it go? Yeah. Okay. So let me, excuse me. Again, let me start with a quick review of Laplace transform. So the way we apply Laplace transform is to take Laplace transform of given differential equation with initial condition. Then, by the way, can you see this screen that I'm sharing?
Yes.
Good. Then you will get equation in two letters, S and capital Y. You solve this equation for capital Y, then you will get capital Y equals something. This right-hand side is an expression in S. Then you take inverse transform to have lowercase y equals whatever. Then you will get unique solution automatically. Good. We are done up to problem number 13. And let me fix typo quickly. Did you see there was a typo in number 7? So some of you sent me an email to fix this typo. I appreciate your fixing this typo.
Stupid.
Look at this number 7.
Stupid. Everything's stupid.
Stupid? No, I'm trying not to be stupid. So look at this number 7. Can you see this screen?
Yes.
Good. In this line number 1, I ended up writing 2 over s minus 3, but that should be 2 times s minus 3.
Mm-hmm.
And then in the line number 2 is correct. 2 over s minus 3, and everything else is correct. So extra credit for those who sent email. And again, whenever you find something wrong or typo, send me an email to get extra credit. Okay. Students are still coming. So for those who just got in, this video is being recorded. I'll upload this in eCampus. You can check it, and you can also check full load as well sometime this afternoon. Okay, so the last section is Dirac delta function. Section 6.4. All right. Is everyone ready?
Ready.
Good. So quick motivation. The reason we care Dirac delta function is that sometimes we want to understand a system where some sudden huge magnitude of force is applied to the system. So for example, you can think of electric circuit where lightning is applied, or some object attached to spring that is struck by hammer, or ball that is struck by baseball bat or golf club, and so on. So Dirac delta function is useful to study such a system and find a solution. So that's why we want to study Dirac delta function. So eventually, we want to study Laplace transform of Dirac delta function, but we need to define what Dirac delta function is. So let me start with unit impulse function. Intuitively, this is given by square. Let me draw a quick picture to give you some idea. So you can think of rectangle. So you can think of piecewise function that gives you some certain rectangle like this. Do you see this rectangle?
Yes.
Good. So let me choose certain number, T0, T0, for the center of the base. And let's say the base of this rectangle is 2a. So this first point is T0 minus a, and then T0 plus a. Then the base is 2a. The key point is that we want to keep the area 1. Then automatically this height is 1 over 2a. So height is 1 over 2a. Then we have area 1. So quick notation is delta sub a T minus T0. So T0 is the center of the base, and A determines the base. Is everything clear so far?
Yes. So far, so good.
Good. There are infinitely many such rectangles or infinitely many such piecewise functions because A and T0 can be any numbers. So we have infinitely many family of infinitely many such rectangles. So here what we do is to take smaller base. So let me draw some bunch of rectangles with a smaller and smaller base. So originally we have rectangle like this. And then you want to take rectangle with a small and smaller base. Let me use color, orange color, to draw even taller rectangle with area 1. The key point is area 1. You can take even taller. Rectangle. Again, the point is you keep the area 1. So imagine you keep taking smaller and smaller base. Then the value will be higher and larger. Probably this value will be unbounded or infinity. Something like this. Actually, you can use limit to find the function that you will get. That's the definition of Dirac-Delta function. So here is a definition of Dirac-Delta function. So the Dirac-Delta function is defined by limit of our rectangles where A is getting smaller and smaller. Remember, A determines the base. The smaller A, the smaller base. So you are taking limit of such a impulse function or rectangles. And notation is delta t minus t naught. So you just delete subscript A. That's the definition of Dirac-Delta function. Okay, any questions so far? Okay, so this function is kind of weird function with the interesting characteristics. So first, this function has value 0 almost everywhere. Whenever t is not t naught, the value is 0. But if t is t0, the value is unbounded or infinity. Very weird function. Number 2, now that we kept area 1, if you take integral, this function will give you the same area, 1. So those two properties determine Dirac-Delta function. So Dirac-Delta function has value 0 almost everywhere, but 1 point. And the area is 1. Very weird function. Okay, and we want to know the Laplace transform of Dirac-Delta function. Actually, we can calculate. We will calculate this. Okay, so here, we once discussed a similar function in part 2. I think it's example 2, problem C. Let's take a look at this quickly. Let's see, where is our note? Okay, so this is page 6 of part 2. Look at this problem C. Can you see this note that I'm sharing?
Yep.
Yes.
Good. So this is part 2, pages 6. And this piecewise function with value 1 on the interval from A to B has the expression in two unit step functions, u of t minus a minus u of t minus b. Let's use this expression to express Dirac delta function. So getting back to our note, so do you see our note?
Yes.
Okay, good. So we are using our previous calculation. This rectangle function has expression unit step function t minus first value t0 minus a. I mean this first point minus unit step function t minus second value. Now that this value is 1 over 2a rather than 1, we need to divide it by 1 over 2a. That's it. So this is expression for this rectangle function in terms of unit step function. Good. So we can calculate Laplace transform of this guy, which is 1 over 2a Laplace transform of this guy minus Laplace transform of this guy. Good. And then we can use second translation theorem to find the Laplace transform of unit step function, which is e to the negative t0 minus a times s over s minus e to the minus t0 plus a times s over s. Well, you may think it's complicated, but eventually we will take limit. Then we will get quite simple expression. So now we want to find Laplace transform of Dirac delta function. So originally, this Dirac delta function is defined by limit. So what we have is limit followed by integral or Laplace transform. But under mild condition, we can exchange the operation. We can take Laplace transform of rectangle function and then take limit. If you remember, in calculus, you studied the condition involving continuity when you can, so that you can change the operation. So we take integral followed by limit. That's okay. So we take limit of this long expression in this bubble. Well, I'm tempted to plug in 0 there. If you plug in 0, we have e to the something minus e to something over whatever. If you calculate this, you will get 0 over 0 form. And you already know how to find limit when you are given 0 over 0 form. Any idea?
L'Hopital.
Yes, L'Hopital's rule. You can apply L'Hopital's rule, or you can take derivative of this numerator in term with respect to a, and then derivative of denominator with respect to a. Now that you are better than me in calculating this limit, let me skip but you will get twice over twice times e to the negative st0. Good. It turns out that Laplace transform of Dirac delta function is e to the negative st0. Good. Now that we have proved this, you don't need to repeat. You just go ahead and use this theorem. Laplace transform of Dirac delta function is e to the negative st0. All right, any questions so far? Okay, and then last page. Before starting our example, let me make a quick remark. So Dirac delta function has the Laplace transform e to the negative st0 as a special case. What if t0 is 0? If t0 is 0, the theorem says Laplace transform of delta t minus 0 is e to the negative s0. What does it mean? Laplace transform of certain function is 1. Do you see it's interesting? It's interesting in a sense that, well, have you ever imagined Laplace transform of constant function 1? So if you take inverse transform of constant function 1, then there is inverse, which is Dirac delta function t minus 0. So it's a quite interesting fact itself. So there is inverse of constant function 1, which is Dirac delta function. Well, this is a quite interesting fact, but we are not going to get into it much. I just wanted to point this out. Okay, and then exercise. So, well, actually, this is just one problem with the two different initial conditions. So the equation is y double prime plus y equals 4 delta t minus 2 pi. We will try two initial condition, number 2 first and then number 1. Okay, if you apply Laplace transform, we need Laplace transform of second derivative, and then Laplace transform of y itself. And then Laplace transform of delta function. Okay, now you replace this first guy by s squared capital Y, s times y of 0 minus y prime of 0, and then copy of capital Y, and then Dirac delta function. 4 times e to the negative 2 pi s. Is everything clear so far?
Yes.
Good. So let's use this number 2 first, because it seems to be simpler. If you use this initial condition, well, where everything is 0, then we can simplify. This is gone, this is gone. We have s squared plus 1 times capital Y is 4 e to this something. Good. And then you solve this for capital Y. So we have some expression in S together with extra exponential function. So it's time to pause to determine which translation theorem you want to apply. First or second?
Second.
Second, very good. We have extra exponential function, this guy. That tells you we need second translation theorem. Good. So inverse form of the theorem says inverse of capital Y is inverse of this guy whole thing. And the inverse form says we need to take inverse of the expression 1 over s squared plus 1 together with unit step function. Then you replace every t by t minus something. And then this exponent determines how much you translate. Any questions so far? Okay, now the table says inverse of 1 over s squared plus 1 is copy of sine. And you take product with unit step function, and you replace every t by t minus 2 pi. That's it. So unique solution is 4 times sine t minus, oops. So you replace every t by t minus 2 pi. This is the unique solution. So we are done for this initial condition number 2. Any questions? I'm still waiting. Any question? Probably you may want to, again?
It looks good.
Okay, thank you. Probably you may want to ask how to distinguish your first and second translation theorem.
Can you go back to that last page for a second?
This one?
Yeah.
Okay. So So you need to distinguish two theorems. You need to know when you apply first translation theorem, when you apply second translation theorem. So here is a quick tip to distinguish them. Let's see. Again, for those who just got in, this video is being recorded. I'll upload this in an hour so that you can check. I'll also upload the note as well. Okay. So first translation theorem versus second translation theorem. So first translation theorem says transform with extra exponential function is translated version in the output. So what you can do is to locate exponential function in the input or output. So this extra exponential function is in input. So you have extra exponential function in the input, then you apply first translation theorem. Second translation theorem says transform of translated version is capital F together with extra exponential function. Now you have extra exponential function. Oops. You have extra exponential function in output. So if you have exponential function in the output, or e to the something times s, then you want to apply inverse form of second translation theorem. I hope this helps you with the distinguishing two theorems. Clear? Any question? Okay, getting back to our note, just one more problem. We want to apply this number one, probably purple. So we want to apply initial condition y prime of 0 is 1, y of 0, no, sorry, y of 0 is 1, y prime of 0 is 0. Okay. So then we will have s squared plus 1 times y equals 4 plus this initial condition will give you one more term, which is s. The rest of the story will be the same as before. So you take, you solve this for capital Y. Then s over s squared plus 1. And that's it. So you take inverse transform. This guy is the same as before. When you take inverse form, you will get the same thing. 4 sine t minus 2 pi, unit step function t minus 2 pi, plus inverse of this guy. If you look at the table, this will give you copy of cosine. Okay, so this is the unique solution. I hope those two examples help you with the last two homework problems and then eventually one problem in the exam. So depending on your major, you may need to apply this direct data function more extensively, but we just focus on some standard examples. Okay, any questions so far? Probably one more remark for this solution, this guy. So look at this product. This is a translated version. You can even plot graph of this unique solution. Oops. The graph of sine guy is curve like this, and it repeats the same pattern forever for each 2 pi. This unit step function will kill everything in the first interval. The graph of the unique solution looks like this: 0 in the first interval, and then suddenly starts copy of sine like this. So this unique solution is a translated version of sine. The graph looks like this. Well, if the exam is offline exam, I would ask you to plot the graph of this solution, but the exam is online, so I will not ask you to plot this. But I just wanted to point out that you can even plot the graph manually because you understand this translation, the translation of sine guy by 2 pi. All right. Any question? Are you with me?
Yes.
Okay. So, well, this is a first time to discuss a section in synchronous way. I think it's not perfect, but I promise I'll make it better. Let's see. Were you able to join chatting? Let's see. How I won't be able to join chatting during the discussion, but next time I'll try to read your messages as well. Okay, I think that's it. So this record is, this video is being recorded. I'll upload this video and note, hopefully in an hour once it's saved. And I'll also post solution of homework 7 and solution of practice exam. So you should practice homework 7 and practice exam as well.
Dr. Lee,
Yes,
the solution for homework 7 is going to be submitted after the Wednesday deadline, correct?
that's right.
Okay. And then also on Thursday, the lecture is not going to be covering topics that will be on the exam. Is that right?
Well, we are done with all the stuff. So on Wednesday, I try to quickly review for this chapter, and then discuss your questions. Depending on how much we do, I'll be holding office hour on Thursday morning.
Okay. Thank you.
You're welcome. Other questions? Oh, of course. I'll be here for office hour today. I think it's from 2:30 to 4:30. So office hour today, and then Thursday morning, as before. Any other questions? All right, if you don't have any further question, well, if you have any question, you can send me an email or you can join office hour this afternoon or later. All right. Thank you very much.
Thank you, Professor.
Thank you.
Thank you.
You.
Thanks. Thank you. Thank you.
Hi, Professor. So
Bye. Yeah.
I have a question real quick for the test. So are we supposed to print the test and then scan the test and submit it?
For the free response problem?
No, yeah, for the test.
Yes. So as you did for homework 6, you take photocopy, you can use a cell phone or a scan or whatever. You
Yes.
upload your file into ecampus.
Okay. And that's it, right?
Yes.
All right. Well, thank you very much.
You're welcome. Bye.
Bye.